Let's learn how to transform and combine random variables. This is what we're going to do. There's really just some rules that we need to remember, and then just some of the notation is funky. We need to introduce some super funky notations. So sigma sub x, sigma sub y, mu sub x, mu sub y. We're going to get a new random variable t that is a combination of mu sub x and mu sub y. It goes all over the place. So it's pretty interesting. All right, so we are going to learn how these things are affected, our mean and standard deviation. So remember in chapter 2,
Yes.
we had those rules, right? If we were adding or subtracting something, it was going to change our mean but not our standard deviation. Right? In other words, it changes measures of center or like where a point is in a distribution. But it's not going to change our measure of spread because if you're adding, it's just shifting your measure of spread, right? So that's just a refresher. When we're multiplying and dividing, it is going to change our measure of center and our measure of spread, right? So remember, if you're doing some sort of a linear transformation on your mean and standard deviation, right? The part that multiplies and adds changes both your mean and your standard deviation. But if you're going to calculate your mean standard deviation, right, you would just use the multiplier. You guys had a test question about that. We went over that. So a lot of the same rules are going to apply. Pete's Jeep tours. Awesome. Funny Jeep tour. All right, so he offers a half-day trip. There's got to be at least 2 passengers on the trip. The vehicle can hold up to 6 passengers. We've got a random variable x is the number of passengers on a randomly selected day. This random variable is also discrete. I think it's good to mention. So if you were to calculate the mean of this, you would come out to 3.75, right? And in order to calculate the mean, we learned in 3.1 that what we're doing is we're multiplying our random variable x times the probability of that random variable occurring. So the way that 3.75 was obtained was by adding 2 times 0.15 plus 3 times 0.25 plus 4 times 0.35 and so on. Right, so that's how that mean was obtained. The standard deviation was the difference of each one of those x values in the mean squared times the probability of x, and those are all added up. All right, just kind of showing them what's going on with them in the box. Okay, so Pete, he charges $150 per passenger. You know, random variable C, that's the amount Pete collects. So his gross, right, on a randomly selected day. So the idea is that if we look at the mean and, rather, if we look at the distribution of his number of passengers and compare it to that distribution of money, right, of the amount of money that he collects. All those distributions are roughly the same, right? So if we look at the shape is about the same. Our center has been transformed by our multiplier, as has our standard deviation, right? So since we have this. Since he's charging $150 per day, right? What's he doing? This is just, all this is the number of passengers. That's the number of passengers times 150, right? So what he's done is multiplied all of the random variables by 150. And what's the result? Well, the result is that your mean is old mean multiplied by 150. And your standard deviation, the new standard deviation, the transformed standard deviation, is this old standard deviation times 150. And the reason for that is that, remember, multiplying affects both mean and standard deviation. She's going to multiply this. I checked it. All right.
So just making sure I know how to do it.
Yes. Aren't I? Well, if I can say aren't I, then why can't I say I are? It's weird. Why is English so backwards? Okay. So here's our rule, the same rule that I was saying. And it's pretty much the same rule that we saw in chapter 2 when we were doing transformations of mean and standard deviation of just data sets. It turns out that those same rules are true for transforming mean, standard deviation, and our random variables for some sort of discrete probability distribution.
I didn't know what to say, so like, I don't even remember what I said.
Alright, so if we add a constant, what do you think is going to happen to your mean? Yeah, it's going to be shifted by whatever that constant is. What do you think happens to your standard deviation? I'm not saying exactly. And so that's what we see if we consider Pete's cheap tours once again. That if we were to look at, I believe we're looking at his net here. His net, or the shape of the distribution between his gross and his net are going to look the same. The mean is going to change, but the standard deviation won't. Whoa, I feel like we passed something. We did not. Okay, that was weird. So same rule here apply with adding. It's not super different from the rule that we're using. Yeah. All right, linear transformations. That's what I was talking about before, right? So we're going to do a linear transformation on this, right? So if we're going to, for instance, right, add something to the mean and then also multiply the mean, what's going to happen? Well, it's going to change by that same linear transformation, right? That's on the mean. All this that we're doing right now is just really taking rules that we learned previously and applying them to some sort of random variable, right? So some probability distribution. All right, so here we go. This is where we get into it. When we're combining our random variables, we come up with a new random variable t.
I was like watching a video of me reading like what I was supposed to say, so that I could. Like,
so
it's ahead, so I was just like repeating.
In this case,
but then it took me so long.
we've got Pete's and Aaron's adventures. Well, Pete's cheap tours and Aaron's adventures, right? So we have a new random variable where we're adding the number of passengers on Pete's and the number of passengers on Aaron's, and we get a new random variable t, for which we can find both the mean and the variance. So these distributions are definitely going to change.
Wow, you're a really good speaker.
It doesn't. Is it good?
Yeah.
So this is just showing you the two
I
distributions
cut out my stuttering.
and their means and standard deviations. We're going to combine them now.
Jump cuts.
I'll go watch.
It's supposed to show like my.
So we can see that if Pete and Aaron were working together, right? And they wanted to know, hey, maybe Pete and Aaron had they were lovers.
That's sweet.
And they decided to make it more than that. And so they joined their businesses together. Yep. So now they want to know, hey, well, how much money do we expect to make from our combined businesses, right? And it turns out that it would be perfectly fine for them to add those two means and say, hey, well, the expected value that we're going to make from our combined companies would just be the sum of the two means, right? The two means. So our two expected values, we can add them together and find the expected value of our new company that was born from love.
I miss my social life. You think so?
All right, so
Yeah. And
again, we talked about independence in the last chapter. And in order for us to do some of these transformations, we're going to have to assume that our random variables x and y are independent.
Yeah, it's a big thing, especially at UNM. Like they have like a BA and B program, which is a pipeline program, but they make you sign a form to like stay in them. It's like a big thing for them to like keep helping their students. Yeah, so. That was probably like the hardest thing I
Okay, so here's a big, nasty table with random variable t, which is x plus y, random variable x plus random variable y. And if you consider all the combinations, which is kind of crazy. Like, so if you interpret this table, you gotta stare at it for a little while, right? You actually have to combine all of them. This is actually all possible combinations. Alright, so you're seeing that we have each one of these going with x equals 2, and then what we're doing is multiplying times each of our possible random variables, or possible variables for y, possible values that our random variable y can have. So what this leads us to is talking about how to calculate the variance of t. What do you notice about the variance of t? So this is how your variance would be calculated. I am almost positive you don't have to do this. That if you're given a problem, you're going to be given the variance of your random variable. Or you'll be given the variance of x, your random variable x. You'll be given your variance of your random variable y. And then you'll be asked to perform some transformation on those, asking what the variance of your random variable t is, right? Now, keep in mind, you can add variances. You may not You can add or subtract variances. You may not add or subtract standard deviations. Okay. So if you need to add or subtract two standard deviations, you're gonna have to find the variance by squaring, then combine, and then bring it back down by taking the square. And so you notice that the variance of t is just your variance of your random variable x plus your variance of your random variable y. That's really what all this is trying to get to the bottom of. But at least you can see how the variance of t was calculated. It's pretty darn complicated. It would be a very, very long bit of calculation to do by hand. All right. So here is the rule. First of all, you have to assume that these two things are independent. And then you are allowed to add variances. Essentially what that is saying. But not standard deviations. I can guarantee you at some point in time, you'll be given a question, and they're going to try to trick you. They're going to try to get you to add standard deviations. But what you need to do is add the variances. It's a very common question. All right, so if we've got two random variables where we're subtracting, it would make perfectly sense that we would subtract the means, right?
I went to Chick-fil-A and they forgot my food.
What doesn't make sense at first, until you think about it, is that if you were going to subtract, so you have a random variable d that is the random variable x minus random variable y. Standard deviation of d is going to be the sum your variance, I should say, of d is going to be the sum of your variance of x and y. So if you're subtracting two random variables, you wind up actually adding their variances.
That's crazy.
It's kind of crazy. But then again, it also kind of makes sense.
Drink. It's cool, but you lose.
All right, so back to our normal distribution. We're going to complete some probabilities. Okay? Just saying that if we combine some random variables, or some continuous random variables, if those random variables are normal, then their combination is also normal. There's really not a lot more to it than that. All right, we did it. Yay! So we'll start next class doing some examples.
You know what you should do? At the end of your classes every day, you should hook up to this speaker and just play Alexa and then ask those students whether they're just playing Alexa singing. And then everyone's just very confused. Get off past your classroom like, what is he playing?